Hi, Dr. Grahame Blackwell here from the Institute for Harmonious Science with a few thoughts about cutting-edge concepts in physics. I've called this video Beyond the Higgs boson because the Higgs theory is by no means a complete solution to the issue that it's about. Even if the possible sightings of a particle at the Large Hadron Collider late last year are confirmed, there are still a number of important questions that need answers. More on this shortly. My own research over the past 15 years has led to a comprehensive view of matter and energy that neatly covers the Higgs issue, almost in passing, as a natural part of an integrated picture. That picture includes quite a few other things too, such as how gravity works and why there's so much more ordinary matter than antimatter in the universe. Both questions that have puzzled scientists for quite a long time. The unity theory is so called because it unites the fundamental concepts of time and space, matter and energy, including light of course, in a way that shows very clearly how they relate to each other. It also unites all of the proven features of relativity and quantum theory in a way that explains exactly how many of those features come about. The Higgs theory says that all of space, including the space around us, is full of particles called Higgs bosons, named after physicist Peter Higgs. The idea is that these particles are responsible for a property of every material object in the universe, the property that we refer to as mass. Now there are three well-known effects of mass. Probably the one that most people know best is weight. In fact, many people think of mass and weight as the same thing. Weight is what happens when the Earth's gravity pulls on the mass of an object, as Newton famously figured out under that apple tree. But of course, even out in space, where there's very little gravity and so things are pretty much weightless, they still have exactly the same mass. And that brings me to a second effect of mass, neatly demonstrated by all those stars and planets out there. Because particularly if things are big enough, not only are they pulled by gravity, they also do the pulling. The more mass a star or planet has, the bigger its gravitational attraction. On a technical note, general relativity combines these two aspects of gravity into one, though it still leaves two effects to be explained. In relativity, gravitation is described as bending of space-time. The bigger the mass, the bigger the dent that star or planet makes in space-time. And weight is seen as a result of the tendency of an object to follow those curves in space-time. The two questions then become, what is it about mass that causes the curvature of space-time? And what's the nature of matter and the nature of space-time that causes the one to follow the contours in the other? The unity theory offers answers to both of these questions. The third effect of mass is what we refer to as inertia. If something's standing still, it takes a force, a push or a pull, to get it moving. Once it is moving, it takes another force to slow it, to stop it, or to make it change direction. That's inertia. And that's the effect, the only effect, of mass that the Higgs theory deals with. It makes no attempt to explain how mass is involved in gravitational effects. The unity theory explains both inertia and gravitation as natural consequences of the structure of material particles. More than that, inertia and gravity are just different manifestations of the same feature of matter as described by that theory. Mass is a central characteristic of the nature of all material particles. There's a lot of scientific evidence that particles of matter could be closed-loop photons of electromagnetic energy, like light wrapped round on itself. This fits, of course, with Einstein's famous E=mc². Matter and energy are the same thing, and with the wave-like nature of particles that we see in quantum mechanics. If we take that quite literally and follow through the implications, all sorts of things drop out quite naturally. In particular, all these effects of mass stand out clearly without any need for other particles or forces. The Higgs theory says that those particles that are all around us and out in space have a sort of sticky effect, as if everything's immersed in treacle or molasses. Those sticky particles drag on objects and hold them back from getting moving. That's inertia. The tricky bit here, though, is that inertia also keeps things moving once they're on the move, so that they need another force to slow them down or to stop them. This means that once something's moving, those sticky particles are keeping it moving, rather than dragging on it to slow it down. So, if I'm standing still, you're driving by at 60 miles an hour, and a rocket is flying overhead at 6,000 miles an hour, it's as if we're all immersed in a giant bowl of treacle. But that same treacle is holding me still, keeping you moving at 60, and keeping that rocket moving at 100 times your speed, all at the same time. Special relativity says that nothing is moving relative to itself, which I think we'd all agree with. So if we look at each separately, we can think of each as not moving, so that treacly effect can act on it, no problem. The problem comes when we look at all three at once. The sort of sticky effect that can keep different things moving at different speeds takes rather more explaining. The unity theory shows very clearly why force is needed to get an object moving, to slow it down, or to change its direction. And it shows exactly why an object will continue at the same speed in the same direction if there are no forces acting on it. Of course, we can't ignore the fact that glimpses were seen at the end of last year of what might have been the Higgs boson. Or, of course, it may have been something else completely. There could be all sorts of things out there that we've not even thought of. And, if you're searching over a very wide area for the very first time, it's quite a long shot to assume that the first thing that you see is the thing that you're looking for, particularly if you don't even know whether or not it exists. If that particle sighting is confirmed, it'll then be necessary to test experimentally whether it can do what the Higgs boson is supposed to do. That could prove quite a bit trickier than spotting a particle in the first place. It'll also be necessary to find another particle. It's known that the particle that might have been spotted wouldn't have enough energy on its own and would need a heavier, higher energy partner particle to work with it. But there's already been a thorough search of higher energy areas, and it's understood that no particles were found in those areas. The unity theory is just that, a theory. But it's a theory backed up by a wide range of experimental evidence from many eminent scientists. And it fits very well with proven results from both relativity and quantum theory. Best of all, it doesn't involve any new particles or fields or anything else of that sort. What you see is what you get. The simplest solutions are always the best, as long as they fit with the available evidence. It's difficult to think of a simpler solution than particles that are formed from photons of electromagnetic energy, like light, but simply wrapped up into very small bundles. And this very simple solution fits all of the available evidence, as you'll see if you watch the other videos that are listed at the end of this one, or if you visit the websites that are also listed at the end of this video.